All right, so we have a circuit here with 3 resistors and 2 batteries. The batteries have different potentials, so different voltages for those 2 batteries, but the resistors are all the same. So they're not given a value in this example, they're just all the same value, okay? The question is, if I have these 5 different areas, what rank from high to low would be the potentials at those different areas, and what would be the current at those different areas? Now, we know we look at potentials across various spaces, so basically what we're doing is what areas are at higher potential than other areas in this circuit for part 1. And then for part 2 is how do those currents look throughout this circuit. Okay, so let's look at part 1. So we know that across this battery we have 12 volts of potential. And across this battery we have 9 volts of potential. So if we imagine that bottom is our lowest potential in the circuit, so 0 potential, it's our reference potential. How does A compare to D? If going across this battery, I would have 12 volts, and going across this battery, I would have 9 volts. Well, we know that A then must have a larger potential than D. And how do those compare to E? Well, E was my reference, my low potential. So we know those are both larger than E. All right. What about B and C? How do the potentials compare at B as they do at C? Well, B and C are on that same space, and they're all connected by that same location, that same, nothing's in between them. And so they have to be at equal potential, and we can write that by those 2 letters being together, or we can say B equals C. So B and C have to be at the same potential. Well, this gives rise to 2 options for our ranking. We know that A is greater than D, and that could be greater than B and C, which we know is greater than E. How do we know everything's greater than E? That was our reference potential. We also know that B and C are greater than E because we have a resistor between them, and so we know the potential drops across a resistor. All right. Or we could have A is greater than BC, which is greater than D, which is greater than E. So how do we distinguish between these 2? We know that A has to be greater than D. We know that A has to be greater than E. And we know that B and C have to be greater than E. Well, how does D compare to C? If we think about the current going from our battery outward, we know that there's a potential drop across D and C. So we know that D has to be greater than C. And so if that's the case, not that one. That's not the right one. This has to be our situation. So the potential at A is greater than the potential at D, which is greater than the potential at B and C, and everything is greater than E. All right, so that's our potential. What about our currents? Now, when we're dealing with current, we need to remember a couple of things. Current along a line doesn't change. So that's the first thing we want to keep in mind. So do we have any currents that don't change along a line in this situation? Well, we do. As I go from A to B, it's all one line. It goes through that resistor line, that squiggly line, but it's all one line. So the current at A has to equal the current at B. Let's just make this clear in case you kind of pop back at this video. This is potential here in green, and we're going to use the blue. This is going to be our current discussion. All right. So we know A has to equal B. We also know that C has to equal D because they too are along a common line. All right, well, what happens between B and C? Between B and C, we notice there is this junction, and that leads to our second thing we have to remember about current. At a junction, the current in has to equal the current out. This is the principle of conservation of charge. So if we imagine the current traveling this way in our circuit, this junction then tells us, and this way in our circuit, this junction then tells us that B plus C has to equal E. B plus C has to equal E. Because as these two come together at this junction, they come into one spot. All right, so we know that E then has to be the largest current. If B and C equal E, this tells us that E is greater than B and E is greater than C, because I need both of them to equal E. So where do we land? We have an option that E can be greater than B, which is equal to A, so E is greater than BA, which could be greater than CD. We have an option where E can be greater than CD, which is greater than A and B. So these two are greater than here. The current out of the 9-volt battery is greater than the current out of the 12-volt battery. Or those two currents could be the same. E could be greater than C, D, A, and B. These are all the same. Are the currents the same through this branch? Through both of these branches. That's possibility 2. So we have 3 possibilities just with our basic examination. So how are we going to figure that out? And then we're going to remember Ohm's law, which tells us that current, we know that the voltage is equal to the current times that total resistance. So the total resistance, the larger the voltage, we have a larger current if the resistances are the same. So our resistance in the whole circuit are the same. So that's it. And again, this is total, right? And I have a larger voltage coming on this side with A and B being the current out of that battery than I do the 9 volts. So A and B is greater than C and D. So that is our answer for the second part to rank the current. So thinking about potentials across and how that really represents where areas of high potential and where areas of low potential to answer that first value. And then remembering these issues with current, that it's along one line, the current doesn't change, and it splits at a junction, and we can't have any loss of current, no loss of charge, conservation of charge principle. And so our current in at a junction has to equal our current out. All right, good job.